Welcome back. In a previous segment, we studied the time complexity of an algorithm to find the largest element in a sequence of integers. In this segment, we're going to do a similar analysis for a different algorithm. So first, let's review the problem and the algorithm quickly since we discussed them before. The problem is to find the location or the index of a target object in a given finite sequence of objects. So this is the description of the input and output of the algorithm. The algorithm is called linear search, takes as input one target object and one sequence of distinct objects a sub 0 to a sub n minus 1 and returns an integer. The variable I keeps track of the current index in the sequence starting at a sub 0 until you have reached the end of the sequence or you have found the target object in the sequence. You go to the next element, and when you have exited the loop, either you did it because you reached the end of the loop or the end of the sequence, or because you found a target. So in the first case, you return minus 1. In the second case, you return the index at which you found the target object. Now let's analyze the time complexity of this algorithm. Remember that in such an analysis, the first step is to identify which primitive operations you're going to count. So what are the primitive operations in this algorithm? Well, we start with an assignment statement here, then we have one comparison, a second comparison. The body of the loop is just a single assignment, and we have one comparison, and that's about it. So the primitive operations are either assignment statements or comparisons. We have to choose which one to count, possibly both. Let's just count the comparisons. The reason for that is because, notice, every time through the loop you have to do this comparison. And actually you have to do that one as well most of the time, so really you have to do two comparisons for each iteration of the loop, and then you do one more comparison at the end. So let's just say we're going to count the number of comparisons. So now the question is, what is the time complexity of this algorithm? Meaning, how many comparisons does this algorithm execute to solve a particular problem of size n? Remember that n is the length of the input sequence, that is the number of objects in the input sequence. And here, even when the length of the input or the value of n is fixed, let's say n equals 5, we have a problem here in computing the time complexity of this algorithm, because it is really hard to come up with a function f of n such that for a given value of n, say 5, returns a single value. In fact, f of 5 is not uniquely defined. Why is that? Well, that's because depending on the identity of the target object and depending on the identity of all of the objects in the sequence, the number of comparisons will be different. For example, if the target object is the first element in the sequence, then this iteration is only going to be executed once, or these comparisons here. So the new problem we are encountering here is that the time complexity of the algorithm, as we have defined it, depends not only on n, but also on a specific input values. So even for a single given value of n, there is not a single time complexity, and therefore the definitions we have been working with so far does not really apply to this case. There's not a single function that will return the number of comparisons for any input of a particular size n. So to solve this problem, we need to define different kinds of time complexity. Let's start with so-called best case time complexity. Notice we just argued that for a given size n of the input to the algorithm, not only there are typically many possible input data of that size, there are many possible sequence of size 5, since you could pick any integers for each one of the 5 elements, and then you could randomly shuffle them in any order. But not only that, the point is that for each possible specific data of size 5, there could be a different time complexity. So now we're going to focus on a special case called the best case time complexity of the algorithm. And that is defined as the function f of n that returns the smallest possible number of primitive operations that are needed by the algorithm to solve any problem instance of a given size n. So to be clear, we still have a function of n. N is the size of the input. But for any particular n, once n is fixed, out of all of the possible instances of size n, this function is going to return the runtime or the time complexity of the instance for which the algorithm takes the smallest number of primitive operations. That's why it's called the best case. It's the case for a given n where the runtime runs or is the smallest. So let's perform the best case time complexity analysis for the algorithm that we've been dealing with, namely the linear search algorithm, which I reproduce here. Remember that the first step in the analysis, which remains the same, is to determine the primitive operations that are going to make up the time complexity. Let's keep the comparisons as the primitive operations of interest. Now the second step is actually to count these primitive operations for a given value n, a fixed value of n, but now we're going to do it in the best case. So remember that this algorithm goes through all the elements in the sequence starting at a sub 0 and stops as soon as it has either found a target or reached the end of the sequence. So what is the best case? In other words, what is the problem instance or a problem instance in which the algorithm takes the smallest number of steps? Well, clearly the algorithm is going to step right away if the target object is the first one in the sequence, and that is defined as the best case. So all we have to do to compute the best case time complexity now for a particular size n is to figure out how many comparisons the algorithm executes when the target object is the first one in the input sequence. So let's see what happens. I is equal to 0 initially, and it's less than n, so this is one comparison. The second comparison is to compare the target object with a sub 0. Now this comparison is going to be false, meaning the target is equal to a sub 0 in the best case. So the algorithm will exit the loop right away after just 2 comparisons, and then there's one more comparison here to determine the output or the return value. In this case, the return value is going to be the value of I, or 0. So in the best case, for a particular size n of the input, the number of comparisons is always equal to 2 plus 1. 2 in the while loop and 1 for the return value. Now notice the interesting thing here is that f of n is a constant value. What does that mean? That means in the best case, when the target object is the first one in the sequence, it doesn't matter how long the sequence is, the algorithm always takes the same amount of time, in other words, the same number of comparisons, that is 3. And as we already know, this is a constant function, so in this case, the best time complexity of this algorithm is big theta of 1. That means it's of order 1, which is just a constant time. So of course, for other algorithms, the best case time complexity may not be a constant function. But let's step away from this specific algorithm and reflect upon the concept of a best case time complexity concept. How useful really is this kind of time complexity analysis? Well, the answer is that it's typically not very useful. because what we're computing here is the runtime of the algorithm in the best case. And typically the best case is not representative of the set of inputs that typically get fed into the algorithm. In other words, the best case is an unrealistic case. It's a very rare case. So we don't really care how fast the algorithm runs in the best case, because the best case is not the most common case. So in short, even though the analysis was easy, the best case time complexity is typically not very important or very useful as a description of the runtime of an algorithm. So let's turn to another type of time complexity called worst case time complexity. I think the meaning of this concept is pretty obvious from its name. Of course, we start from the same observation as before, meaning that the size of the input n is not enough by itself to determine the runtime of the algorithm. So now we're going to look at the worst case instead of the best case. So the worst case time complexity is the function f of n that is defined as the largest possible number of primitive operations that are needed by the algorithm to solve any problem instance of a given size n. So this time, we start with a given constant n, and among all of the possible instances of size n, we're going to find the problem instance for which the algorithm runs the longest, or uses the largest number of primitive operations. And that number is going to be returned by f of n, and that number is called the worst case time complexity of the algorithm. Let's go ahead and perform the worst case time complexity analysis of the linear search algorithm, which I reproduce here again. As always, the first step in a time complexity analysis is to choose the type of the primitive operations you're going to count. Let's just stick with the comparisons as our basic or primitive operations. Now the interesting question becomes, what is the worst case time complexity of this algorithm? In other words, in the worst case, given a size n of the input, how many comparisons does the algorithm perform? Well, we remember the best case is when the target object is in the first position of the sequence. The worst case, of course, is when this loop has to go through the whole sequence before it terminates. So the worst case could be either when the target object is the last element, but actually it's even worse if the object, the target, is not in a sequence, because we have to go one step further to reach the end of the sequence here. So let's compute the number of comparisons that the algorithm will perform in the worst case, that is, when the target object is not in the input sequence. Now remember that the algorithm performs 2 comparisons for each iteration of the while loop. Since there will be n iterations, there will be 2 times n comparisons performed by the algorithm to go through the whole sequence. Now notice, since the target was not found at the last iteration, the condition of the while loop will be executed one more time until this condition is false, which means you have gone past the last element in the sequence. So there's one extra comparison here in the n plus 1 iteration. So let's count that one. And finally, when we exit the loop, we still have to do one more comparison to determine the return value. So we had another comparison here. So in conclusion, the worst case time complexity of this algorithm, f of n, is equal to 2n plus 2, which, as we know, is big theta of n. So in the worst case, this algorithm has a time complexity that is linear in the size of the input. While that is not too surprising, since in the worst case, it goes through all of the elements, there are n of them, and for each element, the amount of work is really a constant time, basically couple comparisons and an assignment statement. So indeed, the worst case time complexity of this algorithm is big theta of n, and in general, the question becomes, How useful is this kind of time complexity analysis? Remember, in the best case time complexity, we were so optimistic that that kind of analysis was not very useful. Here is the opposite. In a worst case time complexity analysis, we are extremely pessimistic. We're only considering the worst possible case. How useful is that? Well, even though this assumption of the worst case is not realistic, because the worst case might be as rare as the best case, this kind of analysis is very useful. Because the advantage of it is that it gives you an absolute guarantee in terms of runtimes. If you can compute the worst case time complexity of an algorithm, you know for a fact that whatever input you give it, your algorithm will never take any more time than its worst case time complexity. So in other words, it actually gives you a very useful piece of information. And in fact, the worst case time complexity of an algorithm is typically the one that is going to be used most often.